Hi everyone, my name is FutureiAI. I'm back again. Today we will learn the details of model training. On the model training page, click here to open the hyperparameter settings page. There are several important parameters here. First is the model, which is the target detection algorithm currently used in this model selection. It loads the mature industrial algorithm YALOV 5S. This algorithm has built-in support for 5 different model sizes. Then refer to the following figure. This line is the name of the model, and this name should be used in the hyperparameter settings, making sure to use all lowercase letters. The following 3 lines correspond to the benchmark performance. The first line is the inference computation, the second line is the inference time on the V100 GPU, and the third line is the map accuracy on the COCO dataset. A side note, because the COCO dataset is an open-source dataset with over 90 categories of everyday objects containing 200,000 images with an average of 7.2 objects annotated per image, this dataset is very complex and challenging, which makes the scores seem a bit low, as if only the largest models can be used. In fact, real-world classification is not as difficult, and smaller-sized models can also achieve good results. In general, for each increase in model size, the network structure becomes more complex and the model's expressive power is stronger, making it suitable for more difficult scenarios. However, both training time and inference time will significantly increase. In practical use, choose the appropriate model based on whether the scenario focuses more on performance or inference speed. In industrial scenarios, the S&M models are very commonly used. The second parameter is the epoch, which is the number of iterations. How to choose the right number of epoch? For the first training scenario, it is recommended to set a larger value, such as 200 or 300. From the tensor board of the loss curve mentioned in the previous lesson, you can observe when the loss reaches its minimum during the training process to obtain a suitable epoch value. Subsequent training in the same scenario can use this value as the initial epoch value, and then fine-tune it according to the changes in loss. If the training machine resources are relatively abundant, you can also always set a larger epoch. For example, increase the initial value by 50, then there is no need to fine-tune the epoch model. The training process will automatically save the results of the iteration with the best performance. The third parameter is the image size, and the 2 commonly used settings are 320 and 640. Other values are recommended only for expert mode use. The choice of image size mainly depends on the proportion of the object to be detected within the image. If the area occupied by the object to be detected in the image exceeds 5%, then 320 is sufficient, otherwise, choose 640. Choosing a larger image size mainly affects the training time and inference time. If speed is not a high requirement, one can simply choose 640 without much thought. The fourth parameter is the batch size. The larger this value, the faster the training speed, but the higher the requirements for GPU memory and RAM. If the model training fails, consider reducing this number. The fifth parameter is the offset, which determines which version of the instruction set will be used when exporting the model. This parameter is only recommended to be modified in expert mode, and it is generally best to keep it at 11 without changing it. Other parameters have minimal impact in our environment and do not need to be changed. Next, let's talk about model fine-tuning. In addition to retraining with the entire dataset, model training also supports fine-tuning existing models with a small amount of data. For example, sometimes we have already trained a model with a large amount of data, which works well in most positions, but performs poorly in specific points. Then we can use the original model as the preloaded weights and collect some data from the specific points with poor performance for fine-tuning. First, annotate the newly collected data for the new position to create a dataset, and it is best to also add some other positions with representative positive and negative example images to the fine-tuning dataset to maintain a balance in the dataset. Then annotate some other data from the new position to create a new test set. Then on the model training page, select the original model here, choose the newly created fine-tuning dataset, select the original test set, and then open the hyperparameter interface, change the epoch to 20. And keep other parameters consistent with the training parameters of the original model. Train and observe the changes in loss and model accuracy in TensorBoard to find the appropriate epoch value. For the specific process, please refer here in the screen. First, you need to record the original model's train loss, val loss, and metrics. Observe the chart changes during this training process to find the suitable epoch that meets the following conditions. the train loss should continue to decrease, and the value does not necessarily have to be less than the original train loss. This indicates that new information has been learned from the fine-tuning dataset. The specific val loss do not significantly increase. It indicates that the new model maintains the performance on the original test set. The map does not significantly decrease, which also indicates that the new model maintains the performance on the original test set. Finally, use the found epoch to retrain. Select the original model as the preloaded weights, reuse the new fine-tuning dataset and the new test set, and after the final training is completed, obtain the new fine-tuned model. Alright, the FutureiAI training course has finally come to an end. I hope everyone has learned how to train and fine-tune a model through this course. Go ahead and give it a try.